Good morning, everyone. Okay, let's get started. Any questions from DEPT? Let's go back and revise what we did so that we can slowly get our brains ticking. The experiment that we were looking at yesterday was the distortionless enhancement by polarization transfer. In this, we were able to understand a few important aspects. You could apply different flip angles concomitantly, meaning that you are having an example where a 180-degree pulse and a 90-degree pulse are applied concomitantly. All the examples that we saw before were either a simultaneous 180 or simultaneous 90. But here, slowly, you are able to understand you can change all this. You have the power of changing the flip angle and the phase for different channels and change delays. And the main reason why this pulse program was actually discussed was that the active Hamiltonian that's being present, which will be a combination of chemical shift and the weak scalar coupling, we were able to understand and appreciate that in the first tau 180 tau, proton chemical shift will not evolve. So therefore, we did not evolve it. And since you're just starting with a 0-degree pulse on the carbon, even until this portion, carbon chemical shift will also not evolve. These were the two things. And what we did was to just therefore evolve this tau period with 2 IZSE after having the first 90 pulse on the proton channel. And as we moved further, after this, the 90 and the 180 pulses were applied, you have another tau delay, yet again where we said the proton chemical shift will not evolve. And we also were able to see that the carbon shift will not evolve because there is a tau 180 tau, so omega SZ will also not evolve. Interestingly, the only other thing that's remaining at this point of time is 2 pi j IZSZ, which during this portion, we started off by trying to say which will evolve. But you will see that after the application of these two pulses, you have created a multiple quantum coherence, which is of the form of 2IXSY. So therefore, during this tau period, proton chemical shift, nor carbon chemical shift, or the scalar coupling will not evolve. So keeping things same. Then you might ask, if things are kept same, why do you end up giving this time? If you do not give this time, then all the previous assumptions would fail, or the subsequent assumptions would fail. So we should anyway give that delay. Of course, the delay achieves many things. For instance, preserving the coherence in multiple quantums so that the J coupling will not evolve, which is the main problem of refocused enough, which results in phase distortion. And as we move further, the last component that exists here after the alpha pulse on proton and 180 pulse on carbon is that you have a tau period where only the scalar coupling, the weak scalar coupling will evolve. And we did not take all the terms after the alpha degree pulse. Since these are two pulses applied in two different channels, we first applied the alpha pulse on I, subsequently we applied the 180-degree pulse. You can do it simultaneously, you can switch them, because what you have here, it's alpha times IY, comma, pi times IX, SX. Since IY and SX commute, you can change the order. I just did the I pulse first, followed by the S pulse. You can always do the S pulse followed by I pulse. The outcome will not be any different, which you'll learn from quantum mechanics. And therefore, you are able to get a term which had a multiple quantum term. And a single quantum term. Since the application of the last pulse, all you have is a delay. And we know for a fact that delays do not end up changing the order of coherence. And since the multiple quantum coherence cannot be detected, we chose not to see that any further. That's what we did. So we applied multiple concepts simultaneously. We applied concepts of tau simultaneously, applied 180. Tau ends up only evolving 2 IZSZ term. Chemical shift gets refocused. That's the first thing that we applied in the initial parts of the DEPT sequence. And another concept that we ended up exploiting, is that during this tau delay, since only MQC is present, weak scalar coupling will not evolve. The third concept that we ended up applying was that just before the last delay, your combination of multiple quantum and single quantum, since no further pulses are applied, only single quantum is further evolved to understand what is the final result. This packs a lot of concepts that we learned step by step in the last month, all at one shot in multiple different dimensions. But gives you an idea that although the density matrix formalism, if you start writing out every term, could be very complicated, slowly you can use a logic and rational just to invoke a few things at a given point of time to make your answer come up rather simply. This is the more smarter way of working rather than doing everything brute force, right? Okay. And at the end of it, what did we see? We saw that the final density matrix for the CH system will be Sx times S alpha sin. The final density matrix for a CH system will be Sx sine alpha. And now, since you have Sx, you have the time evolution of t. So what will happen to Sx? Sx will come up with Sx with cos Sx cos omega s t times sine alpha would be present. Remember, you'll do a quadrature detection, which will ensure that the trace of S plus with the density matrix at this point of time will become exp I omega st times sine alpha. So basically, this helps you get the chemical shift of the carbon. And the most important thing that we started with is that the initial density matrix is weighted by omega I. So therefore, the determination of carbon chemical shift is weighted by the polarization of proton. Therefore, you get a higher signal than just acquiring a direct carbon without proton polarization transfer. Okay. Of course, I'm not writing this explicitly after the last density matrix because we have slowly come to an understanding. If I know the operator, I know how the signal is going to look. Is that true? Because that's what we do for a simple one-dimensional NMR experiment. When you have a 1D, say 90-degree pulse experiment, with an acquisition, we don't do anything. We start with IZ, and then we apply a 90 along Y. Then we say it goes to IX, and we stop right there. We know for a fact during the time evolution, you're going to get exp I omega I t, and cos of pi j t is going to come up if an IS coupling is present. And we know that cos modulation of exp I omega t, this is nothing but exp I pi j t plus exp minus I pi j t divided by 2. And therefore, you know, this is going to just come up as two delta functions centered around omega I split by 2 pi j. So I'm not going to write this anymore. We know that if you get and end up getting an operator, you know how the signal is going to look. So that's what we ended up seeing yesterday for the DEPT for CH. I requested you guys to do it for the CH2 system, which will have an additional cos alpha term, and also for the CH3 term, which will have a cos square alpha term. I hope you guys went back in practice. If not, take the next week to do it. And what you are able to see is that the signal gets modulated across CH, CH2, and CH3, which is now called multiplicity editing. What do we mean by multiplicity editing? If you carefully choose the alpha flip angle as 135, CH3 will be in phase. If you phase them positive, CH2 will be negative. So this gives an additional information to the carbon 1D experiment where you get CH, CH2s and CH3s, where the CH2s will be of opposite phase with respect to CH and CH3. So NMR has the capability of making signals change so that it helps you identify them easier.
Sir, can you explain once again why in that tau delay the chemical shift does not evolve? When the density matrix is 2ix sy minus 2ix. Yes, sir.
Right. Yes. First of all, multiple quantum will evolve with a chemical shift. That's the whole idea that we learned earlier. But if you pay close attention, let me divide it down. Let me write only the necessary stuff here. So you are asking here, you have 2ix sy generated. Your problem is, how is that omega IIZ plus omega SSZ does not evolve? Why is that we are not evolving it? Is your question?
Yes, sir.
I want you to go back and remind yourself of why we said initially omega I will not evolve. We know for a fact that in a tau 180 tau, chemical shift gets refocused. So therefore, in this tau delay, we started with saying this will not evolve at all. Okay, now the next step that happens is that you have another tau 180 tau, which will refocus omega SSZ. So therefore, this component will not evolve with omega IIZ or omega SSZ. Yeah, so that is a smartness that comes in. but you have to leave the time delay. If the tau delay is deleted from it, then you can't make the assumption here or here. So that's a problem. So although you might feel that, okay, nothing happens in this tau delay, can I just delete the tau delay? You can't do such things in NMR. They are carefully tuned to pick up one interaction over the other. Did that make sense?
Yes, sir.
Okay, good.
So why this consequence is called distortionless?
That is something I can't explain until I show the spectrum. So the question that is being raised right now is that why is this called distortionless? What is distortion and what is distortionless? For this, I need to show you an actual spectrum. So what I think I have done when I taught this course earlier, I shall show that to you when I give the data, although I'm not given the data to you guys, is that I think I acquired data for camphor, real NMR data in a spectrometer, not simulation, where I acquired many experiments. For instance, I've acquired proton 1D, carbon 1D, DEPT, all versions, right? DEPT alpha, and then refocused enough. When you end up seeing the spectrum of the refocused enough for camphor in this case, you'd find that the faces of the peaks will not be clean in the refocused enough. Why does that happen? Because the term that is evolving will be of the kind of 2HZCX, which will evolve with J coupling. Since J coupling spans a large range and you cannot satisfy all the ranges, you give something intermediate. When you give something intermediate, it neither satisfies 125 or 200. That means, think about it. The reason why you set these delays, let's go back. The reason why you set such delays is to ensure whenever you have something like this, you set a delay to maximize one part. But if the J is not properly set, you realize this will not completely go to 0. We set the 2 pi J tau to pi by 2 to kill this. But the moment you realize the J is not properly set, you realize this will not go to 0. The moment it does not go to 0, you have other terms that exist that will cause distortions. So that's where the smartness of DEPT comes. Here also such terms exist, but such terms exist in multiple quantum coherence, which will not evolve with the scalar coupling. So even if you misset the scalar coupling, the distortions will not exist. There are, of course, differences, meaning that the comparison that we are doing is 2IZ-SY versus 2IX-SY. So the relaxation terms are still different between them. So lines will be slightly broader in the DEPT, but you will not have any phase distortions. Why do I say this lines will be slightly broader? Because both are transverse, while here one is longitudinal, the other is transverse. So the relaxation phenomenon will slightly be different. If you overlay the carbon 1D to the DEPT lines will be slightly broader. That's a different consequence. That's a consequence that comes because both I and S are transverse. You guys follow what I'm saying? If you see the terms between so if you have to take the simple Rinect experiment, you are talking about a single quantum antiphase term, which will evolve with 2HCCZ. On the other hand, DEPT, you're talking about 2HXCY. So this is a single quantum coherence. This is a multiple quantum coherence. Correct? The reason why we are choosing this is because it will not evolve with this. So any misset J delays will not cause such distortions, phase distortions. Of course, the negative of something like this is that you see both are transverse, while here only one is transverse. So the relaxation properties of the density matrix that you have created, or the elements in the density matrix, will be different. Although this gives distortion less, they'll have broader lines because both are transverse. I'll give an example to show you what is this distortion and how does the DEPT not take it. Anything that you choose in life comes with a compromise. You cannot win every way. We said that we are choosing PT-based experiment over direct carbon 1D, largely because you have a polarization transfer that helps, right? So you do gain from it. But what do you lose from it is the tau delay, which might give distortions in the Rinect. Now we are trying to say, okay, I want to take the polarization transfer enhancement, but I don't want the distortion, but I'm ready to take some line width. So that's how things go. It's always a compromise.
So HZCY, we get an NF, right? we have a
But what evolves during time that gives phase distortion is HCCY. I'm talking about what happens after the first transfer, right? The transfer happens here if you think about it, right? After the 1 hour 2J delay, the transfer has happened, right? Of course, you have a different pulse program until that portion. If you compare 1/2J to 1/2J portion, you're talking about an antiphase single quantum coherence term to a multiple quantum coherence term.
and the broadening and the distortion, are they similar or are they completely different?
So broadening and yeah, that's a good question. Both result. So the question that is being raised is that we are compromising broadening to distortions. So his question is the broadening less than the distortions that you get with phase is probably your question. Both lose resolution. If dispersive terms reduce resolution, relaxation reduces resolution, right? In this case, it happens for small molecules, it happens in such a way that the broadening is not as much. It's slight, but it's not much. I'll show it to you. Once you see the spectrum, you'll be able to appreciate it far better. Phase distortions have a very big problem. You cannot determine the chemical shift maximum properly. Chemical shift is a very important parameter with which people qualify their molecule. The moment you have phase distortion, picking a peak maxima, you'll soon realize it's not the right chemical shift. It'll be slightly moved away from the peak maxima. That's a problem. So people will different chemical shifts of the same molecule. So people do not like as much phase distortions in their spectrum. Okay, we would want to try to avoid that first because your chemical shift will be misreported, which is the most important thing we want to report as spectroscopists. Right? So therefore, we are rather okay taking off line broadening. And since you anyway have the natural line width quite sharp for small molecules, you are ready to take that hit. Right? What is the next question you are about to ask?
Distortion as in we get the thing you were adjusting that day.
That's correct. And in this RINEP case, it cannot be adjusted. In a regular NMR, phase distortion happen for all the peaks, and therefore you can correct for all of them simultaneously. So, okay, we will see that in the hardware part. Here, what will happen since the J delays are misset because you have to take a compromise. And therefore, these phase distortions can never be phased out. It will be phased out different for different J couplings. You can't process it that way. Yes, exactly. You can clean up for some, not for the other. For people who are still not able to follow this, it's very, very close to what's happening in this class. I am teaching somewhere. Okay, I'm teaching at a certain 1 hour 2J delay, assuming you guys will catch up. There are people who catch up very quickly. There are people who catch up very slow. But I'm trying to pitch it right in the middle so that the people who don't catch up also catch up a little bit. The people who catch up easily anyway will catch up. Right? So I'm not catering to the person who doesn't understand at all. I'm also not catering to only to the smartest students in the class. I can't do that. So I take a compromise and I hit the lecture right at the middle. And then see who didn't catch up and then I repeat it. J delay is exactly that. You are not catering to 125, it's not catering to 200. You put it at 170 or 150 or whatever. And remember, there is other issues that come. CH2, CH3, the tau delay will be different to maximize their sensitivity. So there are other complications that come into it. In that aspect, DEPT works very well because during the tau delay, it's a multiple quantum term. So you have very less phase distortions that end up coming. Yeah. Good. Any other questions? Yes.
And when we ignore that multiple quantum coherence term because it does not evolve, are we letting go of some sensitivity there?
Yes, we are. That's what relaxation happens. So the question that is being raised right now is that there is a period where we are letting the coherence sit for a certain duration of time tau as multiple quantum. The question is being asked during this time, does relaxation happen? Of course it happens. That's why lines broaden. That's exactly what I'm trying to explain to you. That's why lines are broader, slightly broader for a DEPT than for the RINEP.
I meant, so in the end, where we just forget about one term because there are no pulses after that.
That's correct.
So we just cancel that term out, right?
We ignore the term. That term exists in reality. You can evolve it. You won't get anything out of it. You will get still. Are you ready to accept the 2IXSY term in this tau delay? Will it evolve with scalar coupling? It will not. But on the other hand, it will not evolve with carbon chemical shift. It will evolve with proton chemical shift. Because whatever you have done in this experiment, you didn't say anything about proton chemical shift here. Here, actually, proton chemical shift will evolve. So this multiple quantum term, if at all anything happens, will evolve with a proton chemical shift. But it's still multiple quantum. I cannot detect it at the end. So it'll be present. I just don't choose to see it. You're losing sensitivity because of that. You're letting go. So as you start, let's say you are 100%. Do you realize you are partitioning the polarization to multiple coherence terms and you are letting something go waste? You're letting it go waste. You started with a certain level of polarization and you keep on dividing it. For instance, here let's say you fully transferred. Here you're dividing it into two terms. Assuming your tau is carefully set, then you completely transfer. But tau cannot be properly set, so you're losing some here. So now taking this, okay, let's assume the pulses are fine. You transfer, let's say 80% remained here. Okay, you're transferring the 80% here. Now from here to here, also you can, let's assume the pulses are perfect and you can transfer it. But the moment you go to this delay, you yet again have another loss. Let's say it's another 80%, right? Now remember, within that, it already went into 50%. So let's say you had an 80% proper transfer here, you had 40% and 40%. Here it's 80% or 40%. So you're already at 32%. So you slowly start losing sensitivity.
Consider how long the pulse program can.
Excellent. I'm very happy that you figured it out. So therefore, you cannot keep adding pulses and delays as much as you want. There'll be a time where you cannot keep adding more. The coherence would have been dead by then. We didn't even factor in relaxation yet. But slowly you realize that you keep on branching stuff out. At one point, you lose sensitivity as you keep elongating the pulse program. That's a compromise that comes in, always. Right? So did you guys understand the point that is being raised? As you keep extending the pulse program, you're going to have losses that are going to happen for every step. So you want to minimize the number of steps that exist. There used to be times where spectrometers did not cater to very good pulse widths. The 90 degree, 180 degree had a lot of off resonance effects. So people wanted to reduce the number of pulses because the pulses were imperfect. Luckily, we live in an era where technology is so good. We can have excellently timed pulses, which are very, very good. Hardware has improved so much in the last 30 years, thanks to radio technology. So we still have very good stuff right now, but people used to try to minimize delays, minimize pulses to get the best information that they could get. Excellent discussion. I'm very happy that you guys are asking relevant questions. So this way I'm also able to discuss other things that are not in textbooks. This is what the course is supposed to do. So ask questions, go read and come back so that we can have this kind of discussion. This is what is making you guys comprehend what's happening in the course. Okay, let's read, go back and relearn what all we did. We started by trying to say, I wanted to understand the proton one-dimensional NMR experiment where you have a 90 degree pulse and you have an acquisition. Slowly, we were able to see that for a bunch of spins that are being present, you'll be able to get the necessary chemical shifts and scalar coupling. Then next thing that we said is that, yeah, all that is good, but when you have too many protons, I cannot see stuff. So can I just do a carbon 1D experiment the same way? We said, yes, that's also possible. And you will be able to get some of this. Maybe you will end up decoupling where you will not get the scalar couplings, but you'll still get the chemical shifts. We were happy. But then this came at a cost of sensitivity due to several reasons. One is the gyromagnetic ratio. The other is the natural abundance. Slowly we realize, okay, fine, the 1D is helpful, but not as helpful. In this part, I'd like to add a terms and condition. When people do one-dimensional carbon experiments, they don't do whatever is drawn here. They do additionally something called decoupling in the proton, which I can't go to in this course. There's something called steady state NOE transfer, which will require another 3 lectures to do. So I'm staying away from it. Since biomolecular NMR does not exploit that aspect as much, I'm staying away. That also gives you the proton enhancement. But for now, you guys can assume that I didn't teach you that and you do not know that. So basically the basic carbon 1D experiment does not give you the proton sensitivity. Just the one pulse carbon experiment does not give you the proton sensitivity. So therefore, what we did was to take it to refocused INEPT, where we were able to improve sensitivity, get the same information of carbon chemical shifts. However, there was a problem. The problem was distortions, which we were able to overcome by smartly doing the DEPT experiment, which in addition to reducing a distortion, also helps with multiplicity editing. Meaning that CH2 comes in different phases. By the way, This aspects exists even for the RINEPT. It's just not unique for the DEPT. Even in the INEPT transfer, these things happen. I just didn't have the time to explain it. Okay. Good. Slowly, I've come from proton NMR to carbon NMR enhanced by polarization transfer, and different pulse sequences that could help you get some exquisite information. So NMR is capable of it, correct? But yet again, slowly you guys will start to realize there will be overlaps of signals also in the carbon NMR. Things cannot work out that easily, especially when you go to biomolecules, the number of protons and the carbons will increase. So how do we solve the problem is the next step. So this, I would call it the need for 2D NMR spectroscopy. Last two lectures, I've already been making you guys understand 1D won't help, 1D won't help. Okay, so today we will see in more detail what's a 2D NMR experiment and why 2D NMR experiment is important. Okay, so let me go here and then let me start. So the need for multidimensional NMR experiments. Let's ask, why is it necessary, especially for biomolecules, is that this is a small molecule. After a lot of mix-up yesterday, let me be careful in what I say. Sucrose has 12 carbons and 22 protons. And the 22 protons, if you get the spectrum, you'll still be able to assign all of them. The lines are really sharp. That's because the molecule is very small. If the molecule is very small, the R2 is short enough, and therefore you'll get sharp NMR lines. Why? Because the line width is dependent upon R2 factor. The R2 is less, you have sharp lines. Okay, things are good for small molecules. But the moment you go to a protein, this is an example of a protein called BPTI, bovine pancreatic trypsin inhibitor. You don't have to worry about it. This is one of the classic cases of proteins that was used in the 1980s to do NMR. And this is 55 amino acids. So something close to 6.5 kilodalton of molecular weight. So you started with 300 dalton of molecular weight, which is sucrose. The moment you go to something like BPTI, you have many more protons, maybe hundreds of protons that are being present, because every amino acid, for people who do not know what's an amino acid, NC. This is a single unit of the monomer of proteins. You have many protons that are present, and the R group will have further protons that are being there depending upon the R group. Glycine, R is H, alanine, R is CH3, and phenylalanine, it's a phenyl ring. And so you have more and more protons that come. So the moment you go to a bigger protein system, you have a lot more protons as you start increasing the size. In addition to increasing the number of protons, the R2 also increases, resulting in increased line width. So for the same 0 to 10 ppm, where the TSP reference was set here, can we see the spectrum of a protein molecule, proton 1D? Are you guys ready for it? So that's what you end up seeing. You went from nicely resolved, sharp resonances for a few protons that are being present. You have more in number, and the line width has increased. Are you guys able to appreciate the fact? Yeah. Line width has increased and the number has increased, making 1D NMR. Now, out of so many NH protons that are being present, they all come around this region. You cannot find them. There are too many, one too many to find. There are NH protons, there are CH protons, there are NH2 protons. There are so many protons below this. You do not know where they are. So quickly you realize, okay, proton NMR is not going to help. Doing carbon is not going to be very different. I don't have the carbon NMR for proteins, but that's not going to be very different. You once again will have 100 carbon atoms. And many of them will have the same C alpha, making it, oh God, so how will we start studying them? So this is where we take it to the next step, where instead of just getting the information of the proton chemical shift, which is a good marker for local structure, we also try to correlate it with the carbon chemical shift. So what do we mean by this? The same structure that we just drew a moment earlier, let me draw again. I'm taking the example of a protein because that's commonly done. It's much slightly more easier to understand than nucleic acid. So I'm going to mostly restrict myself with proteins for these lectures, and we can change as we go. What we are able to do here, previously, you were able to get the H alpha protons, aliphatic protons, somewhere in this range. And there are many aliphatic protons. If you go to the side chain, there is C beta, H beta, C gamma, H gammas, and so on and so forth. There are many protons that are being present. Everything bunches up there because all of them are aliphatic. Some of the aromatic ones come here, but there is phenylalanine, there is tyrosine, there is tryptophan, all of which are aromatic. Even histidine can be characterized at some point as aromatic, meaning that all the resonances come in that region. And you have many of these within the protein, making the resolution not good enough from a proton 1D to study. So at this point, what we start to exploit is that instead of just getting the proton chemical shift, we actually correlate the carbon chemical shift to the proton. So wherever you have a carbon proton 1 bond that exists and the carbon is 13C, you will be able to correlate the proton chemical shift and the carbon chemical shift. We'll see how we execute it later on. I wanted to show how the spectrum looks so that we can motivate ourselves to understand this is important to measure. So what happens if you end up doing the carbon proton 2-dimensional NMR experiment? Immediately you see so many peaks that were clubbed up here start to resolve themselves in the carbon and proton dimension. If you slowly sit and count, you will actually be able to see all peaks that exist. For instance, if you take this proton dimension, proton ppm, you have too many protons that are overlapped with respect to each other. But the 2D NMR, let me erase it. But the 2D NMR allows you to calmly sit and still pick up so many protons that are being there. Do you guys follow that? So for every CH bond that exists, you will get this proton chemical shift and the carbon chemical shift correlated. What do I mean by correlation? Let's say you run a 1-dimensional experiment which gives you proton offset carrier with respect to carrier, and you get a carbon offset with respect to its carrier. You actually do a point-by-point multiplication. So this point will be 0 times 0, 0. 0 times 0, 0. Each point will be multiplied by 0 and 0, it will be nothing. But if you go to peak by peak, you will get a dot. So what you're seeing is something called a contour plot. Instead of seeing a 3-dimensional plot, you're seeing a 2-dimensional plot from the top down. Anything that says a contour, is, you can imagine like a mountain exists there. And we have just taken a projection of the mountain and we are seeing it. Okay, so wherever you see a peak, that indicates, okay, that is a CH bond that has a certain characteristic frequency. So you had so many H alphas, H betas, C alphas, C betas, and so many, and all of them end up resolving. So for this is a carbon proton experiment for the BPTI protein. Same protein as I showed you in the previous slide. It's the same system. Previously, the things that you could not resolve here due to so many resonances being on top of each other, are you guys able to appreciate that the 2D NMR is able to resolve it? So slowly we have accepted, okay, we are able to edit our experiments in such a way that only CH comes. Why are we only biased to CH? Can we also do NH? You can also do NH. Instead of just doing the proton carbon channel, if you do the experiment on proton nitrogen channel, you'll also get it. And the most important aspect of any protein NMR study is to get this experiment. This experiment is called a HSQC. What is HSQC? You guys all know what is SQC, single quantum coherence. H stands for heteronuclear single quantum coherence spectroscopy. So this 2-dimensional NMR experiment is like a fingerprint. I showed you guys an example of an organic chemistry paper where whenever they report a new molecule or any molecule, they have to give the complete assignment of proton NMR, proton scalar couplings, carbon NMR. You go to supporting information, every paper has it. Similarly, for any protein that we end up studying, this HSQC experiment is the molecular fingerprint. We have to make sure if I take up BPTI, the spectrum should look like this. If Jeet takes up BPTI and works in his lab, the HSQC should match. So this is a fingerprint for the protein that will not change at all. And therefore, we are sure our samples are all same. So therefore, he can continue to do studies that he wants, and I can continue to do the studies that I want. And if Vinesh ends up taking it in Trivandrum, the spectrum cannot change just because we did it in different parts of the world. It has to report the same thing. So the nitrogen proton HSQC is one of the most important experiments that's run. Now you may ask, why is it the most important experiment that is being run? It's because you have the HN C alpha CO, the polymer that keeps growing. For every amino acid, there is a unique NH that's being present. And remember, within proteins, you can have multiple number of the same amino acids. An alanine could come 6 times, 5 times, 20 times. But each alanine will have an NH. Except for proline, which does not have an NH, every amino acid has an NH. And my request is, go back and take a look at the chemical structures of amino acids. It'll help. Do that before coming tomorrow so that you convince yourself on that aspect. But take it from me right now, every amino acid has an NH. So therefore, if you take a polypeptide, which has 55 amino acids, you expect 55 peaks to exist here because each NH should give you a signal, making it a molecular fingerprint, except for prolines. Okay. And there are also some amino acids that have a CONH2 side chain. They end up giving the CONH2 at some part. Yeah, there you go. So these are some of them. If you're able to see, they will give the same nitrogen, but 2 different proton shifts. It's an NH2. Each NH will have a different proton chemical shift, but the same nitrogen chemical shift. Okay. You might also see some here. So this is one example where you have a CH2 maybe, where each of the H, we are going towards biomolecules where methylene protons will be chiral. Each of the proton, although they are same, you might think chemically, but they'll be chiral because they'll be looking at a tertiary structure, which is different. So therefore, each of the proton will resonate at a different frequency. They are not identical anymore. And therefore, they'll start to resolve as separate peaks. Not in all cases, but in many cases. They're buried in the core or something. So slowly, we have started to appreciate the fact that, okay, we will be able to take the NH spectrum and the CH spectrum, but the NH spectrum is what is acquired most commonly, also because the 15N labeling is rather cheap relatively to carbon-13 labeling for proteins. So when people end up preparing their proteins, by default, they'll end up doing 15N labeling. Okay, and therefore, are they sure whether they made the right protein? They run the HSQC to see if the protein is already reported. If not, they will anyway have to run the nitrogen HSQC to see how the spectrum looks. There are a few important aspects that we can learn from this HSQC spectrum. You see the proton spans a good chemical shift range. It ranges from close to 6 ppm to maybe around 11 ppm. Remember, all these are the same NHs. Going by your chemistry knowledge, you'll think all the NHs will come on top of each other. They don't. Why don't they come on top of each other? Because each of the NH is looking at a different electronic environment in the tertiary structure of a protein. What is the tertiary structure of a protein? It's a structure where there's complicated arrangement of atoms around every NH that's being present. The arrangement are not same at all. If I ask whether you guys sit the same way in every class, pretty sure you guys to sit with different partners in different classes, right? And the kind of understanding that you get or the distractions you get depends upon the people whom you sit next to. It's something like that. Okay, so each of the proton ends up experiencing a different electronic environment that results in chemical shift dispersion across the proton and the nitrogen dimension. Interestingly, I'll show some examples as we go forward. A protein can be unfolded. Studying the folded and unfolded aspects of protein is very important to understand their function. If you end up unfolding the proton chemical shift range reduces drastically. Which is once again not surprising. If you unfold the protein, many NHs will be exposed to the solvent, experiencing similar electronic environments, thus the chemical shift dispersion reduces. So slowly we are able to understand, oh, so chemical shift is a wonderful reporter of tertiary structure, and therefore if we are able to characterize it, we'll be able to study the biomolecular systems, right? And how do they get their chemical shifts? By doing multidimensional NMR, in this case, 2-dimensional NMR. Okay, we'll see how the 2D is executed tomorrow. But I want to emphasize the fact how 2D is important, which can help you learn many different things. So let's go to the next one. This is an example of another very crucial protein called ubiquitin. For people who know English, ubiquitous just means present everywhere. So this is a protein that's present everywhere in our cells. All the time it's present. It's kind of a housekeeping protein. Any protein that has to be killed will have polyubiquitination happening. Let's say that a cell has to kill a certain protein. What we'll do is to tag it with ubiquitin. It'll have multiple ubiquitins on it. So some other protein will recognize, okay, this has been ubiquitinated, go kill it. So it's such an important protein. Without ubiquitin, survival of the cell takes a serious hit. So I showed you 2 proteins right now, bovine pancreatic trypsin inhibitor, BPTI, which has beta sheets and then one alpha helix, actually two. This is something called a 310 helix. This is alpha helix. These are different secondary structures of a protein, which gives you a certain chemical shift dispersion, as you're able to see. And here I'm showing another protein which also has beta sheets and one fully formed alpha helix. Okay, this is another protein that has been nicely studied, which has 23% helical content, 34% beta sheet content. I've given the primary sequence here just to motivate you guys. And if you pay close attention, this would have only one aromatic amino acid, which is tyrosine. On the other hand, BPTI, although very small, has 4 tyrosines and 4 phenylalanines. Why am I highlighting aromatic amino acids, although I'm not showing the spectrum? Aromatic rings have a very interesting phenomenon that go with it. Since the aromatic ring has a pi cloud, any proton that's close to it has a very drastically different chemical shift. So therefore, if you have aromatic rings in the core of the protein, in the internal part of the protein, the protons that are right next to it gets dispersed a lot. Interestingly, BPTI will have a nitrogen shift somewhere close to water, which is not seen in the spectrum. That's right above an aromatic ring. It has an NH pi kind of interaction. Okay, it has a very drastically different chemical shift. Once again, highlighting the fact that chemical shifts are super cool indicators of what they are next to. Of course, you got to solve the structure to understand all this, but the moment you see an anomaly, it's very interesting to see what's going on, right? Yes.
So I thought like aromatics are at a site because of resonance and they probably are more electronegative that shifts it more downfield. So if in a case where because of the resonance it is increasing the electron density at near that proton, so is it possible that it will be like will that effect be higher compared to the pi cloud thing that you know?
So that's what happens. All the CHs come here, but an aromatic CH comes around 6-7 ppm. That's because of the effect that you're talking about. It's called the ring current effect. Sorry, it's actually called the resonance. Because you have an aromatic CH, it already pushes it downfield due to the electronegativity or whatever you want to call it.
Is that the same thing as the pi cloud thing?
Not really. Here we are talking about the NH, the influence of the NH from the aromatic ring. The aromatic ring chemical shifts come somewhere. But if you have an NH that's close to an aromatic ring versus not close to an aromatic ring, the chemical shift will be different. Okay. And remember, if the NH is above or on the side, the chemical shift will be different again. Generally, for a 55 amino acid protein, getting this kind of nitrogen proton resolution is unbelievably good. And I'm giving the reason why does that happen? Because you have a good number of aromatics present. Similarly, I want to highlight the fact you don't have good number of aromatics present, but you still see a beautiful dispersion for ubiquitin. Why does that happen? It has a very nicely folded structure. So you get chemical shift dispersion if you have a well-folded structure. That chemical shift dispersion gets enhanced if you have more aromatics also. These are the factors that determine the nitrogen proton HSQC, which is the fingerprint for a given protein. Okay, let's take another example. This is called hyaline. I think this binds calcium or something. I forget. Yeah, there you go. It binds calcium. It's a 92 residue protein. So slowly we are increasing the size. I started with 55 and I went to 76. Now I'm going to 92. Okay. And what you see on this side is the folded state of the protein. The same protein, if it's unfolded, you see how the nitrogen proton HSQC changes. The proton resolution drastically reduced. Nitrogen is still okay, but you started to lose many resonances in the upfield and the downfield parts of the spectrum. What do we see from this is that a protein gives specific markers for each amino acid, making NMR an atomistic resolution technique to follow every atom that's being present. And when the system undergoes a change, you can still follow that atomistic changes that happen. I can't currently tell you, but you can literally assign each of this to each amino acid that's being present in the protein. And therefore, if you end up following what is changing, what is not changing, you'll be able to say what's happening to the entire protein. Or unfolds. So you can take the protein and keep on slowly adding urea and see how this chemical shift keeps changing. You can monitor it as a function of urea concentration. And therefore, you'll be able to get the assignments. If you assign the folded protein, potentially you'll be able to assign the unfolded protein in some process. The C1H2s are coming here. They are very well distinctly seen here. They're getting two, for a given nitrogen, there are 2 protons. What I'm trying to highlight is that the nitrogen proton HSQC serves as a very important marker for the protein that you want to study and provides you atomistic resolution. And you can study how does a protein behave in different conditions. This is an example where you have a calcium bound form and a calcium free form. It's not even unfolded. I didn't even put urea, indicating the fact that without the calcium, the protein is not going to happily fold. Yeah. You can also do binding studies. People love to study how a drug binds. Where does the drug bind? The moment if I take a HSQC and say, what are the assignments for which amino acid that peak belongs? If we say we add another drug and only a few peaks move, then can I tell which part of the protein the ligand binds? So that's what people do. This is an example where it's a very, very large protein. I forget even the size of the protein. Okay, P53, as a certain domain of P53 is taken, and probably they're taking a short part of it. I forget the paper right now, but I've given the references, which you guys can go and see. This is the original reference, this is the review reference, where they're taking some cysteines that are being present. Cysteines, C stands for cysteine, I stands for isoleucine, V stands for valine. And they're trying to show, as you titrate actually one protein with another protein, there's actually protein-protein binding studies. You take two proteins, and then you're titrating TAS2 protein with P53. And TAS2 is 15 and labeled. So you're trying to follow chemical shift changes of the TAS2 protein as a function of P53 addition. So this is the example that I was trying to say. The chemical shift changes in a certain way. So therefore, you can literally say which amino acids are being bound at what concentrations. So NMR is super important to understand where does a protein-protein interaction interface come up if you get the chemical shifts. And how do you get the chemical shifts? You run the 2D. You have to run 2D, 3D to get the assignment. But you're able to see the moment you have the assignments in a 2D, you can learn a lot of important things from it. There's a protein-protein example. You can throw a small molecule to understand drug binding with NMR, right? So not just that, you can start using the chemical shift changes as a function of concentration. So here the example is TAS2 was titrated with P53, and as you added more and more of the AD2 domain of the P53, chemical shifts started to change, correct? Chemical shifts are changing. If you see from here to here, there's a certain proton chemical shift, certain proton chemical shift, there's a certain nitrogen chemical shift, there's a certain nitrogen chemical shift. So you'll be able to model or follow change in proton and nitrogen chemical shifts as a function of additions of the other protein, and even try to understand where the binding happens first. For instance, the transition that happens here indicates that this part of the protein binds earlier than something like this. It's very, very important information to learn. Okay, these are just highlights. I'll send this to you. I request you guys to go back to some of these papers just to open and read the abstract and what they mean. Not just that, NMR chemical shifts could also be super helpful towards kinetic measurements. This is yet again the protein ubiquitin, which we just saw a moment earlier, the 76 amino acid protein. And what they were able to do is to get the 2D NMR as a function of time for every few seconds. So they acquired the 2D for every 5 seconds. I'm not going to go into detail how this was done. Generally, 1D NMR takes few seconds. 2D NMR would take several minutes to hours, depending upon the concentration and the labeling. But here they were able to optimize the 2D NMR for every 5 seconds. So they take the protein in H2O, they added a lot of D2O to it. What is going to happen? The NH, when you add D2O, will become ND. Will become ND, right? It's supposed to be an arrow. It should become ND. The moment NH becomes an ND, the resonance gets absent from the two-dimensional nitrogen proton experiment. So what they did is to take it, run the two-dimensional nitrogen proton without much of deuterium, and then they added a lot of deuterium, D2O, into it, and then saw this exchange. Now, what do we hope to learn? The positions where the NH might exchange faster versus slower. I think red is faster and yellow is slower. Sorry, yellow is faster and red is slower. This would give you an idea of which parts of the protein are solvent exposed versus which parts are not. So this was a study that they were able to do, and they did this as a function of time, and therefore they were able to study what happens. Okay, I'm just highlighting many different biophysical assays that are possible the moment you go to two-dimensional NMR experiments. Gives you a lot of atomistic information on what's going on. So we have been talking about chemical shifts over and over again. This is an example of carbon and proton chemical shifts across the 20 amino acids that are being present. For instance, we were talking about N, C alpha, H alpha, and C double bond O, and we are talking about the CH correlation. This gives you an idea of the range of C alpha chemical shifts for alanine and C beta chemical shifts. Alanine will have C beta and H beta 3 because it's a methyl group, not the right way to write it, but it's a CH beta 3. Correct? And what you are able to see is that the alpha chemical shift, depending upon the amino acids, come quite differently. So would the protons. So therefore, if you end up measuring the carbon-proton spectrum for a folded protein, you will be able to get a lot of information from it. Make sense? Okay. Yet again, this will be uploaded. So take a closer look at what is being said. Having spoken so much about proteins, I also wanted to highlight an example of nucleic acids. This is a classic case of a Watson and Crick duplex. You guys might have studied what's a Watson and Crick pair. A pairs with T with 2 hydrogen bonds. G pairs with C with 3 hydrogen bonds. This is an example where the AT is in the Watson and Crick hydrogen bonding. And you see the spectrum of that in red. So red is Watson and Crick. And those are the nitrogen proton resonances that come. So basically the NHs that are being present are sampled right there. And in this sequence, in the core of it, you have 6 of the thymines. To sit and calmly count, you'll count 1, 2, 3, 4, 5, 6. So all the thymines, all of these are all same AT pairs, gives different carbon-proton chemical shifts, indicating subtle differences in the local structure that are experienced with the same Watson and Crick AT pair. Okay? So the same holds good for the GC pairs. This has only 3 GC pairs that are observable. And therefore, you see all the 3 resonances for the Watson-Crick pair as well. In one of the work that I did, fortunately, what we looked at is, what if we change the hydrogen bonding pattern of the adenine to something else, and what happens to it? And slowly you see that the moment the hydrogen bonding pattern is changed, for the T9 nucleotide, where the hydrogen bonding changed, the chemical should change drastically. Okay, yet again indicating subtle changes in hydrogen bonding or tertiary structures. Chemical shifts are super effective reporters of it. Yeah. The same holds good for RNA. I'm not going to repeat the same thing. Go try to take a look at some of this. But the message is yet again same. If you use chemical shifts, you can learn some important information about GC pair, GU pairs, GA pairs, UU pairs, and UG pairs, and AU pairs. The chemical shifts are quite, characteristic of what they end up coming. The same holds good for a CH pair. Due to want of time, I'm just going to let it go. But you can see that the same system, if you end up taking the CH chemical shifts of sugar, you still see a remarkable change that starts coming up. And finally, what are the good and bad of it? The good of it is that you'll get much higher resolution. But the bad of it is that as you start to increase molecular size, your R2 increases. If the R2 increases, lines become broader. So as you go more and more in size, the resonance becomes broader and broader. Therefore, you lose sensitivity and resolution together. So a standing example of this is an protein which has 405 residues. This is the HSQC of it. But you slowly see the resolution is rather poor in the middle because multiple peaks are coming on top. So therefore, what do you have to do? You have to do 3-dimensional NMR experiments. 2D also doesn't suffice. So people can keep on building 2D, 3D, 4D, and so on and so forth. Alternatively, people can also come up with some techniques which improve resolution. There's an experiment called TROSY. For the same system, you see that the resonances are much sharper. Okay. With that, I would like to stop, where you can also see that for a much larger protein. It's called the malate synthase G, MSG, very well studied protein, which is getting close to megadaltons. Right? It's several hundreds of kilodaltons, about 0.8 megadalton. So NMR can also study very large proteins where we end up seeing the methyl groups, which are also effective reporters of what local structure exists within the core. Okay, with that, I would like to stop this lecture and then ask you guys to go back and reflect on the fact on how does NMR help, especially multidimensional NMR, how do chemical shifts on carbon nitrogen would be helpful. Tomorrow we'll see how a 2-dimensional NMR will come up in the pulse program. We'll apply the density matrix formalism and see how a 2D comes. Thank you very much. Bye-bye.